You should be overly knowledgeable about this. Decreasing the concentration, Kevin. Decreases the particles, which would do what? Okay, so let's word that as less frequent collisions. Okay, less frequent collisions. And what would that do to the rate of reaction? Slow it down. Lowers the rate. Okay, so baby steps for me. I want you to show me individual dots that you're connecting. How are they connecting? Decreasing particles, less frequent collisions. Less frequent collisions will lower the rate of reaction. Cool? Next. So concentration is apparently one factor we can change to influence the rate of a reaction. Another thing we can change up is the state of matter. Why would gases react more quickly than solids? Raise your hand.
They have more energy.
Okay, so what kind of energy are we talking about here? Kinetic energy. So more kinetic energy, how does that impact the collision theory? Keep going.
They move more and have a higher chance of, or
You're right, higher probability of, okay, because they're going to be moving faster. So more kinetic energy, the particles move faster, which will increase the frequency. You can say frequency or likelihood, you can kind of phrase that how you want. Frequency of collision, which causes the rate to increase. This is like my special language I'm writing in, but you guys get it, I think. All right, so you can see how kinetic energy plays a role. Kinetic energy, like inherent kinetic energy, or kinetic energy in terms of temperature. Okay, so gases are moving faster, they have more inherent kinetic energy. How would, or why would, decrease in the temperature cause a decrease in reaction rate? There's two things you should say about this one. Yeah.
Particles are moving slower, so there's less.
Okay, so less temperature, less kinetic energy equals fewer collisions. Sorry. Fewer collisions. Okay, and fewer collisions will decrease the reaction rate. There's something else. Yeah.
They'll have sufficient velocity.
Okay. So this one's just simply like, are you going to collide, yes or no? This one's just simply about them making contact. But even if they make contact, maybe they won't have enough activation energy to really get the reaction started. So the lower kinetic energy plays two parts. Lower kinetic energy means slower particles and may not meet activation energy. And if you don't meet activation energy, I don't care if you collide 100 times, you will not react. There's not enough energy to break the bonds, the reactants, to reform product bonds. All right, so far we've got temperature, concentration, and what's something else? Remember, who watched the old TED video with the example of them going to the dance? Yeah. Okay. So tell me what else was in there. Go for it, Kevin. Catalyst. Okay. So the matchmaker, she was like, "Hey, you look good together. You guys should be together. Let's put these two reactants together." And she did it faster than anything else could have. Because why? Why? Hold on. Let me scroll down to catalyst real fast. Why would a catalyst speed up a reaction? What do they do, Michelle? Lanisha? Okay, so catalyst will lower the activation energy of the reaction by, there's something else you have to add to this. Anybody, something about a pathway? Name? Okay.
Creating an alternate pathway.
Right, by creating an alternate reaction pathway. You could call pathway a mechanism too. That's another way of saying it. Okay, so now the pathways, we've actually drawn them before. They're visual. You can see the pathways. What do the pathways look like? You drew them again on your on your simulation. You talked about each part as the reaction was happening. Here's what I'm talking about. Figured I want to put down these things. Thank you, Clayton. Okay. So the reaction pathways look like this. What kind of reaction is that? Exothermic. How do you know? Just by looking at it. High to low energy. It's lost energy, right? So this is potential energy. This is reaction progress or coordinate. There's a couple of names for it down here. So the reactants have a set amount of energy. The products have a set amount of energy. Overall, there was a loss. And so this was what you guys drew on your web quest. You're like, oh, delta H is here. That's the reaction enthalpy, or enthalpy of reaction. And it's negative because it's exothermic. Where is activation energy?
The curve
Okay, so from what to what?
reaction to the top height of the coil.
So the reactance energy here to the tippy top here. Okay, so that energy is right there. That's activation energy. What does a catalyst do to that? Lowers it by allowing for an alternate pathway. So literally the pathway, this one's like da 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 da. This one's gonna go da 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 da. Okay, what is exactly the same though? Enthalpy is the same, so the delta H is the same. The spot where the reaction started and the energy where the products ended is exactly the same. The pathway that it takes in the middle, you don't really know what's going on here. It's like the transition state. There's things bouncing off each other, things changing up, rearranging. But that right there is lower. Therefore, we call it an alternate pathway with the lower activation energy. Okay? So know a lot about this. You'll see graphics like this on my test and on the final exam for this class. Okie dokie, that's why I'm harping on this one. So sum up here, what were all the ways you could alter the rate of reaction?
Increased volume.
All right, hold on. Decrease volume of container. Why would that influence the rate of reaction?
They're hitting each other more because they don't have as much empty space.
Right, so they're closer together, so therefore they have to hit each other more often. What else? We talked about a couple of them. Catalyst. What else? Increased temperature. What else? So increased concentration. What does bracket mean? Molarity concentration, right? So when I say concentration, we're talking about molarity, making sure we're speaking the same language here. And one more thing. They're talking about cliques in the video. The cliques kind of clump together. Okay, so what are you doing to increase surface area? Making it powdered. Okay, that was a misconception on our solutions test, which I will pass back acids and solution tests tomorrow probably. So decreasing the particle size sounds like it's decreasing the surface area. It doesn't. It increases the surface area. Because a block of sugar has how many faces? 6 faces times whatever their area. That's it for their surface area. Powdered stuff, these are tiny, 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 tiny cubes. Well, they all have 6 faces. Sum up all of their faces together, they have more surface area exposed. So more surface area, more area for collisions, more collisions, faster rate. Okie dokie? So we're talking about rates today. What rate did you travel to school today? 60. Woo! 60 what? Kilometers per hour. Okay. So distance over time, right? We don't travel very far. Like maybe you'll go to the sink and back in a lot, right? We're not going to travel a distance, but how would we measure rate of a reaction? It's on your reading guide. Somebody over here? Clayton?
Distance over time.
We don't go distances in chemistry. That's physics. What might we be measuring?
Units over time.
True story. Leave me specifically the units. Anybody? On your reading guide? Amount of reactant, aka concentration, stuff, amount, grams, moles, something like that. We do a lot of massing, right? And we do a lot of concentration stuff. So on your notes someplace, I don't care where, I need you to know that rate for us is described as molarity per second. This is generally how we are writing our rates. Molarity per second, or concentration per second. Because our reactions are fast, usually as well, so we're not measuring in hours, we're measuring in seconds. And I've got like one more graph to show you, and then we're going to start our lab. So a lot of the times we have reactants in our hands. We have them available. We can see the reactants change, so we can measure how fast they change. Sometimes though it's really hard to see the reactants. Sometimes we have to look for formation of products. So it will depend on if the style of reaction we're doing, but we might be looking at quantity of reactants over change in time to see how fast they are consumed. Now consumed does not mean let's like have a picnic in the back. It means just used up, right? Please no picnics on today's lab. We got like some strong acid. I already burned my nose like 3 times this morning, so don't waft it. It's not good for your nose. Or formation of products. So if we see, let's say products we're forming are maybe they're like bright purple or pink. Okay, you can really see the products forming. So sometimes we're focusing more on formation versus consumption. Okay, can I scroll down to this graph? And it's, people who did the web quest, tell me, did you see a graph look similar to that on some of the web pages? Yes, thank you. Okay, my last class was like, oh, I've never seen that in my life, like lies. Okay, so of these, I know they're labeled reactants products. I can see that. But why is this line labeled reactant? Why does it make sense? Logical sense. You're starting, first of all, you're starting off with something, a reactant, and over time is the bottom axis here. What's happening? You're using up reactants, you're consuming reactants, and as you consume reactants, you're making products. Okay, you need to know how to interpret this graph. You need to know how to find a rate from this graph. So we can see that reactants are getting used up all the way over here until they start to level out right here. Let me make this a little easier to see. So they're leveling out, and eventually they will level all the way out like that. Okay, as reactants get used, this is apparently, it looks like a 1-to-1 mole ratio, because every reactant used, you go up by the same slope on the products. Used, go up, used, go up, used, go up, all the way over here. So products, you start off with 0. Does that make sense? Yeah, you got no products to start off with. And over time, the products are being produced, and they will level out. What is this leveling off called? Equilibrium. Good, okay. So this is the equilibrium point where the rate of the forward reaction, which is making products, and the rate of the reverse reaction, which is going backwards, making reacting, and that's where they level off, and they're the same, they're constant. Obviously, these are not the same exact, because they cannot actually vary, but we're going to talk about equilibrium tomorrow. Anyway, you can determine rate from this. So you need to be able to determine rate from a data chart or from a graphic. So from this, what do you notice the axes are? Concentration and time. How would you get rate from that? Okay, so what do you tell me to do mathematically? Moles over seconds or slope? Yeah? So rise over run? Yeah? Math. Yeah, okay. So concentration change over the first 50 seconds of this reaction. First 50 seconds of this reaction. I'm going to go up to the reactants. Maybe. About right there. And you can see I'm going from 0.10 to about 0.05. So what's the concentration change? 50% change, but how much of it changed? 0.05, good. Because we had 0.10 minus 0.05, so 0.05 was consumed over the 50 seconds. Is that 0.001? Somebody calculate from real fast. I don't care. I think that's right. 0.001. So that is the rate. It's changing by 0.001 molarity per second. That's pretty fast, actually. Some of our reactions we're going to do today might actually go faster. They might go slower. But you'll notice here, so you see how steep the slope is first? It's going really fast. What do you think is happening as I use up reactants? What's happening to the slope as I get down here of the red? It's slowing down, right? Because it's getting more flat. So it's faster here, and it starts to slow down as you go this way. It slows down eventually till it's a stagnant rate of change. So this slowing down is simply because we're running out of reactants. The concentration is decreasing, as you can see on the axis here. So all those things to come together into a graph here. We'll talk about a bit more about these. The last thing I want you to do is tell me the reactant or the BCE for this reaction here. Interpret it. Can you see it? How do you know? Tell me how you interpreted that, because that's correct. So how did you know that these were the reactants? Right, because you're starting with them and you're going down, you're consuming them, and how do you know those are the products? Because going up. Do you know something about their slopes? The slope of blue versus red. Okay, so who's faster? Products are forming faster. So reactants kind of have a steady slope down. Products are like zoom, high slope there. It starts to level off. Why does that make sense according to what she said for the reaction of the products? Right, so you're forming the products twice as fast as you're reacting reactants. It's a 1-to-2 ratio. So that makes sense for the slope to be offset like that. Yeah? Okay. Some of it is common sense. You're like, I got this, but it's just new stuff. I want to make sure you're good with that. Okay, so for our lab, we are messing with I'm going to skip that for now. We're messing with two different variables that will influence the rate of reaction. We're going to mess with concentration and with temperature, but we need to kind of get the concentration ones started. The temperature ones are going to take a little while to heat up and cool down, so we're going to let them set to the side for about 20 minutes, and then we will react them. So you don't necessarily need 100 milliliter beakers, but you guys probably will want those. If you don't have them, it's fine. Use 200s or 250s. It's no big deal. The 4 test tubes are because you are going to have 2 reactants, reactant A and reactant B, and they're going to make a product. If I told you reactant A contained iodine and reactant B contained starch, think back to biology. What do iodine and starch make when they come together? What color? Did you ever do something with potatoes? Blue, purple, thank you. Black, blue, purple, purple, blue, black. There you go. All right, so it's going to change a dark color. So that's how you'll know when the reaction's done, because it's going from clear to black. All right, so make sure you know that. Your reactants cannot touch until you are ready to react them. Once they even touch, like one drops touches each other, then make sure that you start your timer. You can use your phones for your timer. Otherwise, the hot bath and the cool bath, remember how to set up a hot bath? What are you going to be using? Hot plate and beaker of water halfway full. Lovely, right? Do not set the setting above a 3 because it will not denature, but essentially messes up, kills the product or the starch. It starts to break it down. It won't work after that. Okay, don't heat it above a 3. How do you make a cold bath? Ice bath. Ice and NA. Beaker, thank you. Just making sure we know that there's just ice chunks going in here filled with water. You will be sharing that across the station with you. Otherwise, I think it's self-explanatory. I just want to make sure that you guys know that you're only going to, it says 5 trials on the heated temperatures ones. So you're not going to do 5 trials, you're going to do 2 trials. Okay? 1 hot and 1 cold. And then the other 3rd trial will be what you are doing at room temperature for the first part of the lab. Okay? So let's get in groups of 3. Goggles and go. The hot plates might still be hot, be careful. Anybody have an extra lab book? Where are these dang lab books going? I need one person, one of the board, because there's 2 groups of 2, and 1 person's fine. I got a hot plate back on the fritz. Yeah, one more. If anybody needs speakers, there's some back here on the rack back here. Yeah? Ask away. No, there's two different activities. This is an activity, the first activity changing. What's activity? The data table in the back is very informative. It'll help kind of lay out instructions a bit better. Yay.
Oh, Shayla, I got you. Sorry about that. I'll get you started.
You're gonna go sit in the back, so you have a calculator?
Yes.